Welcome back to the fourth and final video for section 5.5. We're finally getting ready to put it all together here, what our fundamental spaces have to do with anything. So let's take a look back at solving this system right here. So if we put that into our matrix, or make that matrix into our calculator, and RREF, let's see what we get. Well, I get 1, 0, negative 1, 1, 0, 1, 2, negative 1, and 0, 0, 0, 0. So our answer is x sub 3. Oh, we're going to have a parameter. X sub 3 is t. X sub 2 would be negative 2t minus 1. And x sub 1 would be t plus 1. Okay. Now, I'm going to write this as a t plus 0 down here. And I'm going to write this as another way. How about 1, negative 1, 0 plus t times 1, negative 2, 1. So notice that this guy right here, the 1, negative 2, 1, he was the null space of matrix A. And you'll see that, and maybe we better do this, if we take the matrix A and we multiply by any scalar multiple of this, 1, 3, 5, 0, 2, 4, 2, 1, 0, and if I multiply by any scalar multiple of 1, negative 2, 1, let's do 7, negative 14, 7. Let's see what we get. So we'll get 7 minus 42 plus 35 is 0. 0 minus 28 plus 28, which is 0. 14 minus 14 plus 0, which is 0. So that's what we mean by being in the null space. Any scalar multiple of this guy will get sent to the null or the 0 vector by our original matrix. He acts a lot like what we saw earlier, and we'll come back and let's jump down to that right now. Remember how we saw that the sine of theta was equal to 1. We had theta equals pi halves, but we also saw that sine of theta is equal to 1. If we wanted the general solution, we had pi halves plus 2k pi, where k was an integer. So, and the reason why was because sine of 2k pi, where k is an integer, is equal to 0. So this acts like the null space of the sine function, okay, because it gets sent to 0. So I can add any multiple of this and it won't change the output. So tying it all back in together, what does this tell me? It tells me to make the vector negative 2, negative 2, 1, I would need 1 of the first column plus negative 1 of the second column plus 0 of the third column plus anything that's in the null space, because it will get sent to 0, the null, by the matrix. Let's just do a quick check. 1 minus 3 is negative 2. 0 minus 2 is negative 2, and 2 minus 1 is 0. So literally, negative 2, 1 is 1 times the first column vector minus 1 times the second column vector. So these tell us the linear combination to make our desired guy, if it's possible, and the null space, you can add or subtract any scalar multiple of him and he won't affect the outcome because the matrix sends him to 0, so it won't add or subtract anything from the overall situation. All right, so finally, in section 5.3, I asked, are the vectors x plus 1, x squared minus 1, and x squared plus x in P2 linearly independent? And I asked you to explain and write them as linear combinations of the other vectors if we had any linearly dependent vectors. So what have we learned? Well, x plus 1 corresponds to the vector 0, 1, 1, where these are the coefficients of the x squared, the x, and the constant term. Similarly, x squared minus 1 corresponds to the vector 1, 0, negative 1. And x squared plus x corresponds to the vector 1, 1, 0. And so we can check to see if they are linearly dependent or not. So I'll do k1 times 0, 1, 1 plus k2 times 1, 0, negative 1 plus k3 times 1, 1, 0. And let's check to see if that's the 0 vector. But like we've done before, we'll set up our linear system and let's put them into the calculator in RREF and see what you get. I get this guy when I RREF. And why does that make sense? Well, to make the 1, 1, 0 vector, I could take one of these plus one of those and check it out. So 0 plus 1 is 1, 1 plus 0 is 1, and 1 minus 1 is 0. So that tells me that the third vector is 1, 1, 0 is equal to 0, 1, 1 plus 1, 0, negative 1. But how is that related to what we learned in 5.3? When we solve this system, we get k3 is equal to t, k2 is equal to negative t, and k1 is equal to negative t. Letting t be negative 1, or let's let t be 1, we get negative 1 times 0, 1, 1 minus 1, 0, negative 1 plus 1, 1, 0 is equal to the 0 vector. Moving these two guys to the other side of the equation, you then see that we can solve for the third vector in terms of the other two. And similarly, we could solve for any one of these guys in terms of the other. So we don't have to say that the third one's the linearly dependent one and use the first two. We could say that the second one is linearly dependent on the first and third and use those guys. Well, I hope that's made sense, and go ahead and try the homework, and we'll see you in the next section.